So this video is section 4.2, curve sketching polynomial functions. And this section is really just putting everything that we've been talking about in the previous sections together in order to identify different characteristics about a given function using calculus. So there's going to be kind of two parts to this section where we're creating our own list of conditions given a polynomial equation. And then we're going to sketch from collecting all that information. We're going to sketch a graph of the function. And then the second part is given a list of conditions, interpreting those conditions in order to sketch a graph that could represent the polynomial that's being described. So this looks like a really long list, but it's basically everything that we've been doing in section 3.4. 3.5 is really about absolute extrema and being able to use apply the extreme value theorem to identify absolute extrema, but that'll come back as well. But not just not in this section in particular, because we're looking at polynomials defined over their implicit domain of all real numbers. But we're taking everything we talked about in 3.4 as well as 4.1 in order to kind of compile all of the information about the function that we want to use in order to sketch the graph. So we'll be looking at finding the first and second derivative, from the first derivative, finding critical values of the function, using the critical values to determine where the function is increasing or decreasing, and then from there locating the local extrema, which we can use either the first derivative or the second derivative test. Identifying hypercritical values of a function using the second derivative, and then using those hypercritical values to determine where the function is concave up or concave down. And from there, wherever the concavity is changing, right, those will be points of inflection that give us another characteristic about the graph. And then sometimes it can also be helpful to identify intercepts like x-intercepts and y-intercepts before we sketch the graph. So we're going to look at this first polynomial function. And we first want to identify what the first and second derivative are. So just using power rule, we would have x squared minus 4x plus 3 for the first derivative. And then the second derivative would be 2x minus 4. So to identify critical values for this polynomial function, I'll set the first derivative equal to 0. And this is the first derivative is a quadratic that looks like it can be factored to x minus 3, x minus 1. So our critical values will be at positive 3 and positive 1. And we want to determine where the function is increasing and decreasing. So I'll put our critical values on the analysis line in order. And this is going to also kind of kill two birds with one stone. When we do our test values and see where the function is increasing or decreasing, that's also performing the first derivative test, which will help us to identify where local extrema are. So for test values, I'll do 0, 2, and 4, and I'm plugging those test values into the first derivative. So f prime of 0 would be positive 3, therefore the function would be increasing from negative infinity to 1. F prime of 2 would be, what would that be, 4 minus 8 plus 3, so negative, meaning decreasing from 1 to 3. Oops. And then f prime of 4 would be 16 minus 16 plus 3. So it switches back to increasing from 3 to positive infinity. So I can state those intervals. So increasing from negative infinity to 1, comma, I'm listing them, no union needed. 3 to infinity. And decreasing between 1 and 3. Okay. And from that analysis line, we're able to see there would be a local maximum at x equals to 1. And it's going to be more helpful to us if we know the actual point. So I can plug 1 into the original function. It looks like when I do that, what do I get? I get 1, 7/3. And then it looks like there's a local minimum at 3, 1. I'm plugging 3 into the original function to get the 1. So I can actually plot those points. 3, 1 and 1, 7/3. So 7/3 is 2 1/3. 1 and 2 1/3. It's maybe about there. So I have my local max and local min plotted. And now let's look at concavity. We could kind of get a sketch of the graph from just the given information, but let's go ahead and now, since we can identify more characteristics, let's do it. So to find the hypercritical values, we'll set the second derivative equal to 0. And we get that our hypercritical value would be x equals to positive 2. So we put 2 on the analysis line. Use a different color. And I'll plug in 0 and 3. So f double prime of 0 would be -4. So the graph will be concave down from negative infinity to 2. And then f double prime of 3 would be equal to positive 2. So concave up. So concave down looks like a frown from negative infinity to 2. Concave up looks like a cup from 2 to infinity, meaning there's a point of inflection at 2, and then plugging the 2 into the original function, I get 2, 5/3. So 2 5/3 would be 1 2/3. So 1, maybe about there. Okay. So just putting all of that information together, I already have an idea that at the local max, the graph is going to curve down and be concave down. But knowing the point of inflection, I know where that concavity is going to change to concave up. And then 3, 1 being a local minimum. So that would be a sketch of the graph of this polynomial function, just kind of putting all that information together. Okay, let's look at this next polynomial. Switch colors. Finding the first derivative using power rule. And the second derivative, again using power rule, just taking the derivative of the first derivative And then I want to set the first derivative equal to 0 to identify critical values. And I can factor out a 4x squared is the GCF of those two terms. So I can see that the critical values would be 0 and -3. So putting those values on the analysis line in order and using test values, use -1. And plugging those values in. So f prime of -4 is -64. So we go from decreasing. F prime of -1 would be -4 plus 12, so it'll be a positive value. F prime of 1 would also end up being a positive value because it would be 4 plus 12. Okay, so we can say that the function would be increasing from -3 to infinity. Even though there's a horizontal tangent line at 0, the values are still increasing. As x is getting larger, the y values would still be getting larger as well. And then decreasing from -infinity to -3. And it looks like there's only a local minimum at -3, and then plug -3 into the original function, so -3 comma -15. Which would go off of the graph a little bit, be down here. Okay, identifying hypercritical values by setting the second derivative equal to 0. And putting those values on the analysis line. Choosing some test values. Okay, and then plugging the test values into the second derivative. So f double prime of -3 is positive. So concave up, looks like a cup. F double prime of -1 would be negative. Concave down looks like a frown, and then f double prime of +1 would be positive. So switches to concave up again. So we can say the function would be concave down from -2 to 0, the open interval, and concave up from -infinity to -2, and then again from 0 to infinity. So it looks like we'll actually have 2 points of inflection. At -2, plug -2 into the original function, and we get -2 comma -4, and at 0, 12. Plug 0 into the original function. So -2, -4, and then 0, 12 as points of inflection. Putting everything together, since -3, -15 is the local min, the graph has to curve up. And then the graph switches to being concave down between -2 and 0. But then it switches to being concave up again. So it'll look something like that, where it kind of evens out for a second to go concave up. It might just be careful. I know my graph doesn't really look like it would pass the vertical line test. It's hard to go from concave down to concave up, but it does switch at that point. Okay, so now we're going to do the other type of problem where we're going to interpret, and we've done this a little bit already, but where we're going to interpret this given information and then sketch the graph that could represent it. So whenever I think first derivative, I'm thinking about increasing, decreasing, local extrema. And then second derivative, I'm usually thinking concavity and hypercritical values. So we're given in that first line that f prime of x is greater than 0 for all x. So what that tells us is the function is going to be increasing everywhere. The first derivative is positive for all values of x, from -infinity to +infinity. So I'm just going to make a note of my interpretation. Okay, f double prime, next line, f double prime of 3 equals to 0, and f of 3 is equal to 4. Well, if a value makes the second derivative equal to 0, that means that value is a hypercritical value. So x equals to 3 would be a hypercritical value, and then also being given f of 3 is equal to 4, that tells us the actual point at x equals to 3. So that tells us there is a hypercritical value at, or hypercritical point at 3, 4. And that's also a point we could graph, right? 3, 4. So it's a potential point of inflection. And then the next two lines are giving us information about the second derivative. So we're in that third line, it says f double prime of x is less than 0 on the interval from -infinity to 3. So that tells us on that interval, the graph will be concave down. Looks like a frown. And then this last line tells us that the second derivative will be positive on the interval from 3 to +infinity, meaning the graph will be concave up. Looks like a cup, which makes, putting this together, that means this point will be a point of inflection. 3, 4 will be a point of inflection. So we can draw this, we can interpret this. Since the graph is increasing everywhere, I'm thinking this is going to kind of look like a cubic. Something like that. And this is just a sketch that has to meet these criteria. And this graph does that. Your graph might look slightly different, and that's fine. You just have to have that point. It has to be increasing everywhere, and the concavity has to change at 3, 4. Okay, so we're going to do one more together. Let's use green. Okay. So this first line, so we know it's a continuous function, that's helpful. So there's not going to be any jumps or vertical asymptotes. But this first line basically gives us 3 points. So we know the point -1, 2, 0, 1, 1, -2. And we could actually graph those 3 points. -1, 2, 0, 1, 1, -2. That's helpful. The next line is information about the first derivative. G prime of 0 equals to 0 and G prime of 1 equals to 0. So 0 and 1 are critical values, or the points, right? Because we were given information about those points are critical points. So I'm just going to say critical values, but they're critical points since we know the actual point of 0, 0, and 1, negative 2. So that means that those 2 points might be local extrema, and we have to see. They might not. And then the third line gives us information about the second derivative. So g double prime of 0 is equal to 0. Interesting. 0, 1 is a critical point and a hypercritical point. Right? 0 is a critical value and a hypercritical value. So that should be 0, not 0, 0, 0, 1. Okay, so that tells me that I bet 0, 1 is possibly a point of inflection, right? It's either an extrema or, no, it can't, it could be. It's either a local extrema or a point of inflection. And then 0.5 comma 0, that's just another point that we're given. And we can graph that point. Okay, so next we're given information about, the last 2 lines are giving us more information about the second derivative. So we're given that between 0 and 0.5, g double prime of x will be less than 0. So on that interval, the graph will be concave down. Looks like a frown. And then for x strictly less than 0 or x strictly greater than 0.5, the graph will be concave up. Which means concavity is changing on those at 2 points. So there's 2 points of inflection. And it's maybe a little bit easier to see if I made the analysis line with the hypercritical values. We're given 0 as a hypercritical value, but I believe 0.5 is also a hypercritical value because concavity is changing there. So positive concave up on the outside and then concave down between 0 and 0.5. Now, that's all helpful information that tells us that this point will be a point of inflection. Let me use another color. Point of inflection, and so is 0, 1. Point of inflection. Okay. And let's see. So that tells us something about those. Okay. And, since 1, negative 2 is also a critical point, right? We know what's happening now with 0, 1. But 1, negative 2 was another critical point, right? 1 is a critical value, so it's potentially a local minimum. So we're not given other information like about where the graph is increasing or decreasing, but we could use the second derivative test or interpret the second derivative test. So since 1 lies on the interval from 0.5 to infinity, that means that g double prime of 1 would have to be a positive value, meaning that critical value lies on an interval where the graph is concave up, which by the second derivative test makes 1, negative 2 a local minimum. So the graph at 1, -2 will have to curve up. We have point of inflection here between 0 and 0.5, or where the graph changes to concave down. And then we go concave up from -infinity to 0. And then, so -1, 2 is just kind of an extra point that we have. It tells us kind of how steep their graph is right there, but it's not really a special like a special point. Okay, so that's a sketch.